Hello students, welcome to my channel Arun's Physics Portal. In this lecture, I will discuss some multiple choice questions on units and dimensions. These questions are meant for NEET and JEE mains aspirants. It is assumed that you are familiar with the theoretical part of units and dimensions. NEET और JEE मेंस के एग्जाम में मल्टीपल चॉइस क्वेश्चंस होते हैं जिसके 4 आंसर्स दिए होते हैं and we have to check which answer is the correct one. You can take the correct answer only if you know how to solve the given question. In a nutshell, you have to solve the given question and see which is the correct answer out of the given 4 options. Please note that to find the dimensional formula of a given physical quantity, you must know at least one equation in which that physical quantity appears. If you know a large number of equations in which that physical quantity appears, you can use any one of them to arrive at the dimensional formula of that physical quantity. We will see this while solving the problems. Okay? So now let us come to the topic. In the first question, you are required to find the dimensional formula of thermal conductivity. The 4 options are given here, A, B, C and D. So we will use the relevant equation to find out the dimensional formula for thermal conductivity. Okay, I will solve the question and show you the correct answer. इसके बाद आपको क्या करना है, इस आंसर से जो मैंने निकाला है उससे आपको देखना है कि इन दिए गए ऑप्शन में से कौन सा ऑप्शन से हमारा आंसर मैच करता है एंड यू शुड टिक दैट आंसर. क्लियर? और यही प्रक्रिया आपको सारे क्वेश्चन में करनी है. मैं हर एक प्रॉब्लम को सॉल्व करूंगा, उसका करेक्ट आंसर निकालूंगा और आपको ये मैच करना है कि दिए गए ऑप्शन में से कौन सा आंसर सही है. ओके, हियर वी हैव this equation which is relevant in this connection. So let us see what this equation means. So we have a conductor of cross section area A. So this is your conductor of cross section area A. Okay, this end is at temperature theta1, this is at temperature theta2. Distance between these two faces is d and the heat flows in this direction from this face, from the left face to the right face. The amount of heat that flows between two faces is q in time t. We know that to show that we are interested in its dimensional formula, we put the quantity in square brackets. So in this equation, we put every quantity in a square bracket. Okay, so this is k equal to qd upon a times theta1 minus theta2 into t. So put these quantities, different quantities in a square brackets here. So q is the amount of heat that flows between the two faces of the conductor, left face and the right face in time t. So because heat is a form of energy and energy nothing but work done. So work done is F into D, force into displacement. Force is mass into acceleration into distance here D. The dimensional formula for mass is m, that for acceleration is L e to the power minus 2, and for d we have here L. So this is m L square t to the power minus 2, and this is equal to q. So dimensional formula for q is m L square t to the power minus 2. For A, we have L square, area is length into breadth. Both of them have the dimension of length. So this is L square, theta1 minus theta2. These two are temperatures. So the difference of two temperatures is a temperature. So this is measured in Kelvin. So this is the dimension for temperature here, K. For time T, we have here capital T. So when simplified, this gives you the dimensional formula for thermal conductivity as ml t to the power minus 3 k to the power minus 1. Okay. In the next question, you are required to find the dimensional formula for Young's modulus of elasticity. Now, what is Young's modulus? Young's modulus Y is defined as longitudinal stress upon longitudinal strain. Okay, this is the ratio of two quantities. Stress is nothing but force per unit area. So suppose we have here a long rod being suspended from a fixed rigid support. The initial length of this is capital L, and when a force is applied at the free end, the length increases by a small l. Okay, the force is applied here, F. The area of cross section of this is suppose A. Area of cross section is A. So this is stress upon strain or longitudinal stress upon longitudinal strain. So this is force is F, area of cross section is A. So this is longitudinal stress, longitudinal strain. This is change in length by original length. So this is F upon A upon a small l upon capital L. So this is what we have written here. So this gives you the value of y as F dot capital L upon A dot small l. Okay. So to find the dimensional formula, we put the quantities in square brackets. So we have y equal to F dot L upon A into small l. So for force, the dimensional formula for force is ml t to the power minus 2. Force is mass into acceleration, as we have just now seen here. So force is mass into acceleration. For mass, we write capital M. For acceleration, we write L to the power minus 2. This we have seen just now in the previous question. So this is ml t to the power minus 2. For L, this is L here. Area is L square. This is length into breadth. Both length and breadth have dimension of length. So this is L square. And this is L. So this is L here. So this L cancels with this one. This goes in numerator. So this gives you the dimensional formula for Young's modulus as m L to the power minus 1 t to the power minus 2. Okay. Now the next question. Here we are required to find the dimensional formula for angular momentum. The options given are A, B, C, and D. Okay. Angular momentum is defined as moment of momentum. So suppose if we have a body of mass m moving with a velocity v, then its momentum is p equal to m times v. Okay. The moment of momentum is known as angular momentum. So the angular momentum of this momentum p around this axis is given by L equal to r cross p. Okay. So where r is the distance of this particle from this axis. Distance means the perpendicular distance. Okay. This is the distance r. This is the momentum of the particle p. Then moment of momentum is angular momentum, and this is given by r cross p. Okay. If this angle is theta, then r cross p will be rp sine of theta. The magnitude of the angular momentum is rp sine theta. Clear? Because sine theta is a pure number, is a known dimension. So we write here L as simply equal to mvr. This is r into mv into sine of theta. Okay, we drop sine theta from this expression because sin theta is a dimensionless quantity and is a pure number. So we write L as MVR. Clear? So to express the fact that we are dealing with or we are interested only in its dimensional formula, we put this in square brackets, each quantity in square brackets. So we have L within a square bracket is M, V, and R, each one in a square bracket. Clear? For mass, we write capital M. For velocity, we write L t to the power minus 1. For R is the distance. For distance, we write here L. So after simplifying this one, we get the dimensional formula for angular momentum as m L square t to the power minus 1. Clear? In question 4, we are required to find the dimensional formula for a specific heat capacity. And we have the 4 options given here, A, B, C, and D. So this is your relevant equation, Q equal to mc into theta 2 minus theta 1, where Q is the amount of heat given to a body of mass m and a specific heat capacity C that raises its temperature by theta 2 minus theta 1. So from here we have C equal to Q upon m times theta 2 minus theta 1. If we are interested in dimensional formula, we put every term of this equation in square brackets. So this gives you this result here. Every term here is in square bracket. So Q, as we have seen, is nothing but the energy. And energy is nothing but work done. The dimensional formula for work done is also the dimensional formula for energy is m L square t to the power minus 2. For mass here, we have capital M here, and for theta 2 minus theta 1, which is the difference in temperature. So difference in temperature is also a temperature. Okay? It has dimension of temperature. So this is measured in Kelvin, so this is K here. So when simplified, we get the dimensional formula for a specific heat capacity as L square T to the power minus 2 K to the power minus 1. This can also be written as m to the power 0 L square T to the power minus 2 K to the power minus 1. This is so because m to the power 0 is equal to 1. Okay? So if this is given in the option, you can also write this one or tick this answer. Okay? In the next question, we have to find the dimensional formula for gas constant R. Here also, we have 4 options given, A, B, C, and D here. So from the gas law, we have PV equal to nRT. Okay? So I equal to PV upon N into T. P the pressure. Pressure is force by area. The dimensional formula for force is mL T to the power minus 2. Area is L square. So this is m L to the power minus 1 T to the power minus 2. So for P, we write here m L to the power minus 1 T to the power minus 2. For volume, we have L cube. Volume is length into breadth into height. The length, the breadth, and the height all have dimension of length. So this is L into L into L, that is L cube here. This is number of moles, dimension is mole, and this is temperature measured in Kelvin. So this is K here. So when simplified, you get the dimensional formula for the gas constant as m L square T to the power minus 2 mole minus 1 K to the power minus 1. Okay? In the next question, you are required to find the dimensional formula for charge Q. The options are A, B, C, and D. We know that the current is defined as rate of flow of charge. So if a charge Q flows in time t, then current is Q upon time t. Or we write it as Q equal to I into T. As usual, we put the quantities in square brackets to indicate that we are interested in their dimensional formula. So capital Q within square brackets is I within a square bracket and time t within square brackets. So for I, we have current, the dimensional formula for current is I, for time it is capital T. So dimensional formula for charge is I into T. Since m to the power 0 is 1, L to the power 0 is 1, we can also write the dimensional formula for Q equal to IT, and this is also equal to m to the power 0, L to the power 0, I into T. Okay? Next, we have to find the dimensional formula for potential V. We have the four options given here: A, B, C, and D. So we know that when a current I flows in a wire of resistance R for a time t, the amount of heat developed in the wire is given by the formula H equal to I square RT. Since I equal to V upon R, where V is the potential difference across the ends of the conductor and R is resistance, we can write the above equation, this one, as H equal to I into IR into T, I V into T, or V equal to H upon I into T. Okay? I into, this is T, small t. Okay? So for dimensional formula, we put them in square brackets. So this is now V equal to H upon IT. H is the heat, heat is a form of energy, and the dimensional formula for energy is m L square T to the power minus 2. So this is here. I is the current here. Dimensional formula for current is capital I, and for time is capital T. So when simplified, this gives you m L square T to the power minus 3 I to the power minus 1. जैसा कि मैंने पहले बताया, किसी फिजिकल क्वांटिटी का डायमेंशनल फार्मूला निकालने के लिए किसी ऐसे इक्वेशन का पता होना जरूरी है जिसमें वो फिजिकल क्वांटिटी आती है। यदि हम एक से ज़्यादा ऐसे इक्वेशन जानते हैं तो हम कई तरीके से उस फिजिकल क्वांटिटी का डायमेंशनल फार्मूला निकाल सकते हैं। इस एग्जांपल में देखिए, वी हैव टू फाइंड द डायमेंशनल फार्मूला फॉर द वोल्टेज हियर। ओके, वी नो दैट द वोल्टेज एट ए पॉइंट is nothing but the work done in bringing a unit positive charge from infinity to that point. If plus q unit of charge is brought from infinity to a point and the work done is W, then the potential here is equal to W upon Q. Q चार्ज को ट्रांसफर करने में W वर्क करना पड़ा, इसलिए यूनिट चार्ज को ट्रांसफर करने में work done is W upon Q. Okay, so the dimensional formula for V is equal to dimensional formula for W upon dimensional formula for charge Q. For W, we have m L square T to the power minus 2. For charge, we have dimensional formula I into T. So this gives you here m L square T to the power minus 3 I to the power minus 1. You see from here that this and this are the same. These two are the same, even though they have been derived by different methods. So this is what I meant when I said that to derive the dimensional formula for a physical quantity, you must know any equation in which that physical quantity appears. So this has been derived by using the heating effect of current, and this has been derived by using the concept of potential at a point. So these two results are the same. So what would be the method of arriving at the result? Is independent of the process you use. The only thing is that you should know at least any equation in which that physical quantity appears. Okay. Next, we have to find the dimensional formula for the capacitance C. We have the four options given: A, B, C, and D. We know that the capacitance of a capacitor is defined as C equal to Q upon V. Okay, or C equal to Q by V. Q is charge. The dimensional formula for charge is I into T. And that for V, we have just now seen, that is M L square T to the power minus 3, I to the power minus 1. So this, when simplified, gives you the dimensional formula for capacitance as M to the power minus 1, L to the power minus 2, T to the power 4, and I square. Okay? In the next question, you would find the dimensional formula of the resistance R. The four options are given here: A, B, C, and D, and you have to choose the correct one. We use Ohm's law, according to which the resistance is defined as ratio of voltage upon current. So we put them in square brackets to indicate that we are interested in finding the dimensional formula. So R within bracket is V upon I. For potential, we have just now seen the dimensional formula is M L square T to the power minus 3, I to the power minus 1. For current, we have I here. So if you simplify this one, we get M L square T to the power minus 3, I to the power minus 2 for the dimensional formula of the resistance R. So if you compare this solution with the options given here, you see that the second option, the third option, C, is correct. Okay. Now, find the dimensional formula of the resistivity rho of a material of a wire. This is the next question. The options given are A, B, C, and D as usual. So now, the resistivity of the material of a wire is defined as rho equal to Ra upon L. Where R is the resistance, A the area of cross section of the wire, L is its length. So we put the quantities in square brackets as usual. So rho within square brackets is equal to R A upon L. Each one enclosed in a square bracket. The resistance has a dimensional formula we have just now seen: M L square T to the power minus 3, I to the power minus 2. Area is L square. This is dimensional formula for area. And this is the length. This is represented by L here. So if you divide the numerator by denominator, you get the dimensional formula for resistivity of a wire as M L cube T to the power minus 3, I to the power minus 2. Okay. Next, we come to find the dimensional formula of the permeability mu of a medium. It is followed by four options here as usual. So the permeability mu appears in Ampere's law. What is Ampere's law? Ampere's law is this one. Okay. Delta F is mu times I1 delta L1, I2 delta L2 sine theta upon R square. So from this expression, we have the equation for mu as delta F R square upon I1 delta L1, I2 delta L2 sine theta. Or the dimensional formula for mu is expressed by this equation, where each quantity is put in a square bracket. So this gives us the dimensional formula for permeability as mu equal to this one. So we have delta F is the force. So for force, we write ml t to the power minus 2. This is r square, this is distance square, so this is L square, this is I1 delta L1. For current, we have I here. For delta N1, this is small length, this is given by L. Similarly, for I2 delta L2, we write I into L. So this, when simplified, gives you the dimensional formula for permeability as ml t to the power minus 2 I to the power minus 2. This is your option D here. Okay. Next, we have to find the dimensional formula for permittivity epsilon. The question is followed by 4 options A, B, C, and D. The permittivity epsilon occurs in the Coulomb's law of force between 2 point charges, namely F equal to 1 upon 4 pi epsilon Q1 Q2 upon R square. And this gives you epsilon as 1 upon 4 pi Q1 Q2 upon F into R square. Now we put each quantity in square brackets as usual to indicate that we are interested in their dimensional formula. So this is that format. I have omitted 4 pi from here because 4 pi is a constant and it has no dimension. Clear? So epsilon is here Q1 is the charge, Q2 is charge. The charge has dimensional formula I into T. So we have for Q1, IT is here, for Q2, IT is here. Okay? This is the force. The dimensional formula for force is ml t to the power minus 2. For r square, this is L square. So when simplified, this gives you the dimensional formula for epsilon as m to the power minus 1, L to the power minus 3, t to the power 4, I square. Okay? Next, in this question, we have to find the dimensional formula for the coefficient of self-inductance L. It is followed by 4 options A, B, C, and D as usual. Clear? Faraday's law of electromagnetic induction states that whenever there is a change in magnetic flux linked with a coil, an EMF and hence a current as well, if the circuit is closed, is induced in it. Mathematically, we express it as a small e stands for back EMF is minus L di upon dt, where L is the coefficient of self-inductance. This is equal to minus E times dt upon di. Okay? We put the different quantities appearing in this equation in square brackets to find out its dimensional formula. So, L is equal to minus E times dt upon di. This is simply showing, this negative sign simply shows that this is a back EMF, nothing else. So, for E, we have m L square t to the power minus 3 I to the power minus 1. This is the dimensional formula for EMF or voltage. Clear? dt stands for time, so this is t here, and di stands for current, so this is I here. When simplified, this gives you the coefficient of self-inductance as m L square t to the power minus 2 I to the power minus 2. Okay? Next, if the velocity, time, and force were chosen as the base quantities, what will be the dimension of mass? So far, we have seen that mass, length, and time are chosen as the base quantities. The question says that if we choose the velocity, time, and force as the base quantities, then in that system, what will be the dimension of mass? The options are given here. Okay? So let us see how this can be done. We have force is mass into acceleration. So this is mass into, for acceleration, we write velocity by time. So mass is given as force into time by velocity. Put each quantity in square brackets to indicate that we are dealing with the dimensional formulae. So this is given by this equation here, where every quantity is given in a square bracket. So dimensional formula for mass is equal to dimensional formula for force into dimensional formula for time divided by dimensional formula for velocity. For the force, we have F here. It is given in the question. This is the base quantity. Time is the base quantity. So this is T here. And velocity is the base quantity. So this is V here. So the dimensional formula for mass in the new system will be Ft v to the power minus 1, where V stands for velocity. Clear? Next, a gas bubble from an explosion underwater oscillates with a period proportional to p to the power a, d to the power b, e to the power c, where p is the static pressure, d is the density, and e is the total energy of explosion. Then you have to find the value of a, b, and c. Okay? So the period of oscillation depends upon pressure, density, and total energy of explosion. We assume that the period of oscillation is T. So T is proportional to P to the power A, D to the power B, E to the power C. This is given. So T is equal to K times P to the power A, D to the power B, E to the power C, where K is a constant. We put different quantities in a square brackets here. K is a dimensional constant. So put the values here in this equation, put dimensions of different quantities appearing here. So for T, we write m to the power 0, L to the power 0, T. Okay. For pressure, pressure had dimension m, L to the power minus 1, T to the power minus 2. The power is A here, so this is A here. This is density. Density is mass by volume. So this is m upon mass by volume. This is m upon V. This is m upon volume is L cube. So this is m L to the power minus 3. Okay. So we write here m L to the power minus 3 to the power b here. Okay. And this is energy. Energy is nothing but work done. So this has dimension m L squared to the power minus 2 to the power c. So add the powers of m, L, and t on the right side. So this gives you m to the power 0, L to the power 0, t equal to m to the power a plus b plus c, L to the power minus a minus 3b plus 2c, and t to the power minus 2a minus 2c. Now, the equation is correct. The dimensions of m, L, and t on both sides of the equation must be the same. So we equate the dimensions of mass, length, and time on both sides. So dimension of mass here is 0. On the right side, this is a plus b plus c. So a plus b plus c is 0. Next, the dimension of L is 0 on the left hand side. On the right side, this is minus a minus 3b plus 2c. So minus a minus 3b plus 2c is 0. And third dimension of t is 1 here. And that on the right hand side is minus 2a minus 2c. So minus 2a minus 2c is equal to 1. So if we solve equation 3, 4, and 5, we have here 3 unknowns and 3 equations. You can find the value of a, b, c from here. So when we solve them, we find the value of the a, b, c as a equal to minus 5 by 6, b is half, and c is 1 upon 3. Okay, this is how we solve them. Now, the next question. In this question, you have to find the value of 1 kilogram meter square per second square in gram centimeter square per second square. 4 options are given here, and you have to check which option is the correct one. Okay. So we have 1 kilogram meter square per second square is 1. 1 kilogram is 1000 gram. 1 meter is 100 centimeter. So 1 meter square is 100 centimeter square, and this is per second square. So this is 1000, and this is a square of this. So this is 10 to the power 4, isn't it? This is 1000 into 10 to the power 4 gram centimeter square per second square. So this is 10 to the power 3, this is 10 to the power 4. So this is 10 to the power 7 here. So 1 kilogram meter square per second square is equal to 10 to the power 7 gram centimeter square per second square. Okay. Next, Young's modulus of steel is 19 into 10 to the power 10 Newton per meter square. We have to find its value in 9 per centimeter square. The options are given here. So first we write the dimensional formula for Young's modulus, and this is y equal to m L to the power minus 1 t to the power minus 2. Now this is 1 Newton per meter square. So this is your 1 Newton per meter square. This is 1 Newton by meter square. Newton is the unit of force. 1 Newton is equal to 1 kilogram into 1 meter per second square. Okay, upon meter square. So this will give you how much? This is, see here, this is given here 1 kilogram, 1 meter, 1 second to the power minus 2 upon 1 meter square. So this 1 meter cancels with this 1 meter here. So this becomes here 1 kilogram into 1 meter to the power minus 1 into 1 second to the power minus 2. And 1 dyne per centimeter square. Dyne is the unit of force in CGS. So this is 1 gram into 1 centimeter into 1 second to the power minus 2 upon 1 centimeter whole square. So this is equal to 1 gram into 1 centimeter to the power minus 1 into 1 second to the power minus 2. Okay. So divide one by the other. So 1 Newton per meter square upon 1 dyne per centimeter square is, divide this by this here. Okay. So here we have 1 kilogram by 1 gram. So we write here. Okay. This term in the numerator cancels with this term in the denominator. So this cancels out. Okay. This is 1 meter to the power minus 1 upon 1 centimeter to the power minus 1. So we write it as 1 meter by 1 centimeter whole to the power minus 1. 1 kilogram is 1000 gram. So this is 1000 gram by 1 gram. 1 meter is 100 centimeters. So this is 100 centimeter upon 1 centimeter to the power minus 1. So this gives you gram, gram cancels out, centimeter, centimeter cancel out. So this gives you 1000 and this gives you 100 to the power minus 1. That is, this is equal to 1000 into 100 to the power minus 1. This means this is equal to 1000 by 100. So this is only 10 here. This what we have written here. Okay. So 1 Newton per meter square is, bring this to this side. This is 10 dyne per centimeter square. Clear? And hence 19 into 10 to the power 10 Newton per meter square is 19 into 10 to the power 11. Why 11? Because we have here 1 Newton per meter square is 10 dyne per centimeter square. So 19 into 10 to the power 10 Newton per meter square will be equal to 19 into 10 to the power 11 dyne per centimeter square. Clear? We move on to the next problem. 1 joule in another system of units in which unit of mass is alpha kilogram, that of length is beta meter, and that of time is gamma second is. So we have a different system of units in which the unit of mass is alpha kilogram, that of length is beta meter, and that of time is gamma second. So you have to find the value of 1 joule in this new system. The answers are given here A, B, C, and D, and you have to check which answer is the correct one. So we have 1 joule. Joule is the unit of energy. 1 joule is 1 kilogram meter square per second square. In the new system, let 1 joule is equal to 1 kilogram meter square per second square. Let's assume that this is x times. For kilogram, we write alpha kilogram. For meter square, we write beta meter square. For per second square, we write gamma second to the power minus 2. Okay? So we get the value of x as 1 alpha to the power minus 1, beta to the power minus 2, gamma to square. Hence the magnitude of energy in the new system will be 1 alpha to the power minus 1, beta to the power minus 2, gamma square. Okay? Next, the velocity of sound in a medium depends upon its pressure and the density of the gaseous medium. Then you have to find the velocity expression for the velocity of sound in the gaseous medium by the method of dimension. So assume that it is given that velocity depends upon the pressure of the gas and density of the gaseous medium. We assume that V is proportional to P to the power A rho to the power B, or V equal to K times P to the power A rho to the power B, where A and B are the dimensions of P and rho respectively, and K is a non-dimensional constant. Clear? Now, write the dimensional formula for different quantities in equation 1. For dimensional quantities, what we do? We put the quantities in square brackets. Because K is a non-dimensional constant, it is omitted from this expression. We write here within bracket, square brackets, V equal to within bracket P to the power A within square brackets rho to the power B. So write the dimensions of V, P, and rho on both sides. For velocity, we have Lt to the power minus 1. For pressure, pressure is force by area. So that is gives you m L to the power minus 1 T to the power minus 2 to the power A here. Density is mass by volume. So this is m L to the power minus 3 to the power B. Or we can write here, add here m to the power 0, because this makes no difference to the result. This is quantity is simply equal to 1. So m to the power 0 L T to the power minus 1 is equal to m to the power A plus B. M to the power A here, m to the power B is here. So this is m to the power A plus B, L to the power minus A here, and minus 3B here. So this is minus A minus 3B. Here we have t to the power minus 2A. Left side we have t to the power minus 1. Now, for this equation to be correct, we must have the dimensions of m, L, and T, and both sides of the equation the same. And therefore, if you equate the dimensions of m, L, and T on both sides, first equate the dimensions of T. So on the left side, this is minus 1. On the right side, this is minus 2A. So minus 2A is equal to minus 1, or A equal to half. Okay. Next, A plus B gives you 0 here. So B equal to minus A, and this is equal to minus half because A is half. So B is minus half. Put these values of A and B in equation 1. We get the expression for the velocity of sound in a gaseous medium as V equal to K P to the power half rho to the power minus half, or this is equal to K times root over P upon rho. Power half means root over, and power minus half means 1 upon root over. So V equal to K times root over P upon rho here. So this is nothing but this is K times P upon rho. power half, this power half, this is K times root over P upon root. So this is the result. The next question we have the SI and CGS units of energy are joule and erg respectively. We are required to find out how many ergs are equal to 1 joule. Answers are A, B, C, and D. These are the possible answers, and you have to find the correct one. So we write the dimensional formula for energy. This is mL squared to the power minus 2. So 1 joule is 1 kilogram into 1 meter square into 1 second to the power minus 2. And 1 erg, this is the unit of energy in SI. This is in CGS. And 1 erg is 1 gram into 1 centimeter square into 1 second to the power minus 2. Hence, divide one by the other. 1 joule upon 1 erg is 1 kilogram, 1 meter square, 1 second to the power minus 2 upon 1 gram into 1 centimeter square into 1 second to the power minus 2. So this 1 kilogram is 1000 gram by 1 gram. We put it together here. 1 meter means 100 centimeter by 1 centimeter, then whole square. This term cancels out here. So 1 joule upon 1 erg is equal to 10 to the power 3. This gram cancels, centimeter cancels here. So this is 10 to the power 3 into 10 to the power 4 because this is 100 square. This is 10 to the power 4. So this is 10 to the power 7 and therefore 1 joule is 10 to the power 7 erg. Clear? Next, find the dimension of A and B in this given equation. P plus A by V square into V minus B is R into T, where the symbols have their usual meaning. The options are given here for the two quantities A and B. So in this given equation, we see that we are adding A by V square to P, and two quantities can be added only if they have the same dimension, isn't it? Therefore, A by V square must have the dimension of pressure. Therefore, A by V square has the same dimension as that of P. And so A will be equal to P into V square. Being it here, dimension of P is m L to the power minus 1 T to the power minus 2. V square means L cube ka whole square. So this is m L to the power 5 T to the power minus 2. Again, in the given question, we are subtracting B from V. V is the volume. And we are subtracting B from V. And therefore, B must have dimension of volume. Therefore, dimension of B is the same as dimension of V, and this is L cube. So A has dimension m L to the power 5 to the power minus 2, and B has dimension L cube. Clear? Next. According to Einstein's mass energy equivalence, mass m can be converted into energy. The energy E thus obtained depends upon the mass m and velocity of light c. The relation between E, m, and c using the method of dimension is which of the following? Okay, Einstein said that mass can be converted into energy, and the energy that is produced from a mass m depends upon the mass that disappears and the velocity of light. You have to find the relation between E, m, and c. So we assume that energy is proportional to m to the power a, c to the power b, or E equal to k times m to the power a, c to the power b, where a and b are the dimensions of m and c respectively, and k is a non-dimensional constant. Clear? Now write the dimensional formula of all the quantities in equation 1. So what we get? We get dimensional formula for E equal to m to the power a, c to the power b. Put them in square brackets. So for energy, we have m L square t to the power minus 2. For mass, we have m, this is m to the power a, and c is the velocity. For velocity, we have L t to the power minus 1 whole to the power b. So this is m to the power a, L to the power b, t to the power minus b. Now, if the equation is correct, dimensions of m, L, and t on both sides of the equation 2 must be the same. So equate the dimension of mass, length, and time. On the left side, dimension of m is 1, and that of mass on the right hand side is a. So we have a equal to 1. Okay. Next, dimension of t is minus 2 on the left side. It is minus b on the right side. So b is equal to 2. Put the value of a and b in equation 1. We get a equal to k times mc square. Clear? So this is the relation between energy liberated when a mass m disappears. This is known as Einstein's mass energy equivalence relation. I have given a large number of problems for you to practice. Answers to all these problems are given at the end. So these are the problems for you. I hope you enjoy going through them and solving them. So these are the problems here. The answers are given at the end. I assume that you like this presentation. यदि आपको मेरा यह प्रेजेंटेशन अच्छा लगा हो तो इसे लाइक करें, शेयर करें और मेरे चैनल को सब्सक्राइब करें. So thank you for watching. See you next time with some other topic of interest. Till then, goodbye.